Welcome back, everyone. So we are continuing on here with crystal field theory, and I'm on the slides. I'm just trying some different things. I'm keeping the slides in their original color here, just to try something different to see if it looks better on this on the final screen. Just kind of goofing around a little bit. So the last video you should have watched shows you how the d orbitals split in an octahedral complex. And I'm going to rewrite those, and actually you can record what's called that splitting pattern on the back side of that handout from chapter 19. I think there's some gaps in like a big white space there, and you can just put those there. That's fine. I don't want to have you memorize all these things, and I'll rewrite these on the one of the blank slides as well. So in that video where I showed you how the d orbital split, I went through all this stuff, all this material. It's quite a bit on this one slide, so you might just want to spend some time copying it down. I'm just going to kind of go through these verbally, point by point, and you can copy them down. That's fine. And then we're going to go and do the same thing for tetrahedral and square planar, not in that much detail. And then I actually give you trigonal bipyramidal to try for a homework problem. It's kind of interesting. Plus, if you get frustrated and you can't figure out how the d orbitals would split in a trigonal bipyramidal, you can Google it. And I even say that in the homework problem. You can Google it and then you can explain why the pattern exists the way it does. Okay. This particular subset of coordination compound chemistry is called crystal field theory, CFT. So here are the basics. These are just generic notes. Okay, so you don't have to. I mean, you don't have to write all this down really quickly. You can just write it all down at once if you want to. So the ligands are the ones that have the electrons that form the bonds. Great. And what they do is they actually repel, because they are all electrons, the non-bonding electrons, and those are all d electrons on the central, and it should really be central transition metal, but that's kind of understood at this point. They repel them. Okay. Well, how they repel them depends on the geometry. And we just did octahedral, so you get two d orbitals go to a higher energy level, and three orbitals stay at the lower energy level, the EG and the T2G. Fine. So you get them split into different levels. That's the general idea, and I'm going to do, I guess I can write this. So we've already done that one. I'm going to do this one and this one right now or in a few minutes, and then you will be left on your own to do trigonal bipyramidal as an exercise in your homework. It's just a good thought experiment to go through, and I'm not really hammering on this topic too much, but it is kind of interesting. So you get the splitting of the d orbitals. Fine, okay. Then you put the electrons back in there. Now, we're only going to talk about this next part in relation to d orbitals. So you go through the electron configuration, you figure out how many d electrons you have, that's fine, and then you redistribute them in those now split orbitals. Here's the difference. If you have a ligand that doesn't split the orbitals very much, you put one electron in each orbital, low and high, because there's not much of a gap. Then you go back to the beginning. If you have a ligand that really splits, puts a big gap in between the low and the high levels, then you fill the lower part first and go to the top. How do you know which one's which? Well, those are called high spin and low spin. Actually, strong field ligands make a big gap. Weak field ligands make a smaller gap. And I think the handout kind of tells you which ones are strong and weak. And I'll try to let you know, choose ones from the extremes so that there's no ambiguity, or I'll let you know to consider it a strong or a weak field ligand. There's a lot to digest here. Oh, I already said this. Okay, size of the energy difference depends on the ligand. Oh yeah, okay, it's on your handout. It's called the spectrochemical series. Not a great name, but that's what it's called. So if it's weak field, small gap, fine. And that's called high spin. So you unpair all the electrons first. Okay, and because it's a small energy gap, it's a lower energy photons absorbed. So this is information you're going to want to apply all of this through your homework. It takes a little while to get all these puzzle pieces put together. And then if it's a strong field ligand, you have a large gap, and that's called low spin because you put all the electrons into the bottom and you're maximizing the paired electrons. So that's going to be your job. Okay, I'll stop saying that and let's get to the point here. Okay, so we did octahedral. And so let's see, how can we start to do this? So on that handout, you can write this on there on the back of the handout if you wish to. So if you wish to do something like octahedral d orbital splitting, or maybe that's too clunky of a title. Maybe you can just say octahedral because it's obvious. All of these are d orbital splitting. And you don't have to go through and label everything with the detail. You can if you want to. We made the argument in the last video that the orbitals that lie between the axes are the lower energy. And those are called the, I'm not worried about this, the T2G level. The orbitals that are on the axes are repelled more because there's more direct interaction. And so you have the dxy, the dyz, and the dxz in the lower energy. You have the dx squared y squared and the dz squared. Those are your higher energy. And that's called the E sub G. I didn't write that very well, but it's E subscript G. And then the energy gap, what we're talking about, is this delta. And that's called the crystal field splitting energy or the crystal field stabilization energy. And for this, in this case, we would use the subscript octahedral. So it's the crystal field splitting energy. Okay, so crystal, you can write that down if you want to, for octahedral. And if it's a weak field ligand, it's a small gap. If it's a strong field ligand, it's a big gap, and you simply put the two sets of orbitals farther apart. And then you fill in the electrons like the last slide said. So I'm not going to go into that anymore, all right? So I'm going to kind of streamline this. So that's octahedral, and I think I need some more space. And again, you can copy this on your handout so that you have it there ready to go, and you don't have to be responsible for knowing if it's a strong or a weak field ligand, which again is given to you in the spectrochemical series. Let's do the derivation of another one, and then you can write down what you want here. So tetrahedral. Okay, well, what's going on there? Well, it's interesting. Again, I'm not going to go through this in great detail, but what I'm going to do is, so if we have our, like we did before, we just write our generic Cartesian coordinates. And I'm hoping I'm doing this in the same order that we did before, but if I'm not, it doesn't really matter that much. It doesn't really matter in general. I think we did X, Y, and Z before. So if it's tetrahedral, where are the ligands? In octahedral, we put a ligand at the end of every axis. So we put a ligand, well, just on the Cartesian coordinates themselves. Well, tetrahedral doesn't really work that way. Tetrahedral is 109.5 degrees. So where are we going to put the ligands? Well, the easiest way to think about it, I think, I spent a long time trying to figure out how to do this, is using your dashes and your wedges. So you'll have a ligand in between the X and the Z axis. You'll have a ligand in between the Y and the X axis. And then so all of these are in between the axes because of that 109.5 degree angle. All of them. Again, remember, tetrahedral is just ML4, and we also have square planar, but we're going to get to that later. Okay, so in tetrahedral, the ligands are between the axes. So what do you think is going to happen to the splitting pattern? So you have orbitals that are on the axes and orbitals that are between the axes. How do you think those 5 degenerate orbitals are going to split? Answer, the exact opposite way of octahedral. You'll have 2 in the lower and 1 in the upper. So the answer here, now that you've gone through that logic from octahedral, the splitting pattern is exactly the opposite. And this would be delta for tetrahedral. That's kind of interesting, isn't it? So if you understood the octahedral that I went through in a fair amount of detail, then tetrahedral, no problem. Okay, and again, if you want to, and everything else applies. If it's a strong field ligand, it makes a big gap of delta. If it's a weak field ligand, it makes a small gap of delta. And if it's a small gap, you put one electron in each box and then start over. If it's a strong field ligand, you fill in the lower set of orbitals, split orbitals, and go. Okay, you get the idea. So if you want to write this on the back of your handout, you can do that. So that's tetrahedral. So octahedral, tetrahedral, you don't really have to memorize these, but you probably won't need to refer to the diagram right now. Square planar is a little bit more difficult, and I think I give a homework assignment where I ask you to explain this, which is fine. So I'm not going to talk a ton about it, but it's a good exercise to go through. So square planar. Going through the exercise again. Ligands repel the d orbitals. It depends on the geometry. So how are we going to draw this? Well, let's x, y, and let's keep it simple. If it's x and y, and it's square planar, we're going to have a ligand, a ligand, a ligand, and a ligand, because it's all square in the same plane. Let's make life easy on ourselves. Let's call that the x-axis. Let's call that the y-axis. And guess what? I'm just putting a dash here for the z-axis because there's nothing on it. There aren't any ligands there. Okay. So what? Okay, well, the orbitals that are on the x and y axes are going to be repelled the most. Take a look at the diagrams of the d orbitals. Which one do you think is going to be repelled the most? Which one do you think is going to go the highest? Well, it turns out, in this pattern, you're going to want to probably just write this one down. The one that gets repelled to the highest energy is the dx squared y squared. All of that electron density is on the x and y axes, so it's repelled the most. Okay, well, the one that's repelled a lot, but not quite as much, is the dxy. The one that's repelled some is the dz squared. I'm going to rewrite this diagram, by the way. So you get this line of them, 1, 2, 3. So 3 orbitals by themselves, and then 2 that are repelled the exact same amount are at the bottom. Are the, sorry, this is really messy, the remaining ones, the dxz and the dyz. So the crystal field splitting pattern for square planar, again, you can write this down, is this. 2 orbitals at the base, and then 1, 1, 1. So it's 2, and then again, you would follow the rules here. Now, this one we're not going to talk about much. In fact, there's not a whole lot to say about this one. And we're going to do some examples in class. I'm not going to do those here, I don't think. I mean, you can try them, but I'm not going to do them now because this video is going to get too long. I just want to do the basics, and then during class, we'll do the problems. And I may have a video for a sample problem, but let's take a look here. Yeah, so we're going to do these. Great. You can try these on your own. Go through. The book has some great examples, but let's not do all of those right now. If I need to record another video with a sample problem, we'll do that. But in this case, I just want to, yeah, here's one where you have to pull some ideas together, and we'll talk about that later. All right, let's wrap this up. This is just a content lesson, so we're not doing problems in this one, just giving you the basics. So on your handout, you want the splitting patterns for octahedral, tetrahedral, and square planar. The trigonal bipyramidal will be an exercise I will leave you for the homework. So practical notes. Okay. Great. The only one we have to worry about the splitting is octahedral. So if it's tetrahedral, always high spin. It's always a small delta. You don't get much of a separation of the orbitals there. So just fill all the electrons, bottom to top, and then start over. So those are high spin, small delta. So you don't have to worry about the strength of the ligand, if it's strong or weak field. Square planar, you might recall, only occur in special cases, and those are D8 complexes. Okay, what does that mean? So, well, you're only going to get diamagnetic. Remember, diamagnetic means, what does that mean? That means all the electrons are paired. Go back to the square planar and put 8 electrons in it. 1, 2, 3, 4, 5, 6. Yep. If you only have 8 electrons, guess what? All of those electrons are going to be paired up. What's going to be empty? The top orbital, the dx squared y squared. Kind of going a little fast there, maybe. Those are always diamagnetic. Special case, not going to worry about too much. Like I said, we're only going to be concerned with the weak and strong field as it relates to octahedral. Those are the vast majority of the problems that are out there, octahedral. So we're just going to keep this simple here. We'll do this as a lecture with no problems in it, and then we'll do some problems in class. But this should give you enough to at least take a whack at the homework. Okay, good work. See you next go around.